what you do is you ignore a lot of this isn't exactly how it works, but the right way to think of it is to think of particles that arrive with too much delay, you think of them as noise. So in other words, if particles are too far out of where you wanted them, you just give up on trying to classify them as having come from a certain arrival.
So you can partition the molecules into the ones that arrive soon enough versus later.
That's right. And furthermore, what you then do is for those molecules that you give up on, you can treat them as I think you can treat them as Poisson.
And Qj was the probability of having a delay of length j.
Correct.
And this sum.
This sum is funny to me, so I don't really understand why this happened. And unfortunately, my student, she finished her master's and then left. So to be honest with you, I don't. It's not that I don't understand the result. I can follow through all the steps, but I don't have an intuitive grasp.
But what would it look like
means.
if you had a continuously distributed first passage time, f of x? This would be the integral.
It would be the integral of the integral.
Y going from 1 to maximum of the integral of x going from 0 to y.
Something is funny about this because
it's a convolution of.
It's basically convolving with itself kind of thing. So
No, it's convolving with a step function of a given length.
Okay, yeah.
Otherwise, it would be squared.
That's right.
So if Q is fairly compact, if there's only a small range of delays, over which this happens, then there'd be one limited case.
That's right. So our one of the intuitions we do have about this is that this is pretty good if there's like one dominant delay and the rest of the delays are very small, and in particular when m is small. This is a pretty good solution. Okay, this I'm going to skip over. But I'm going to come back to this question. So what is the best you can do? What have we done? We have bounded the capacity of this channel. So in other words, we've come up with some closed form expressions firstly, we took the ideal model and we came up with some closed form bounds on that capacity. So this gives us an idea, if we plug in realistic parameters, of roughly what is the best that we can do. The absolute best possible performance of molecular communication. So I'm going to say something a little bit controversial here, and basically give you my best guess to order of magnitude of probably what the capacity is, at least as far as not trying to do something like passing DNA with some kind of inscribed message on the molecule. So this is just like simple molecules using timing, plugging in realistic parameters, plugging in realistic values for the parameters, and I would say the capacity is probably on the order of about a bit per second. So
for any diffusion mediated.
Okay, so this is where it gets controversial. What do I mean by that? So basically, if you plug in distances like a micron or so, you plug in diffusion coefficients like I think realistic is probably between 1 and 10 micrometers squared per second. You plug in those kinds of numbers, the numbers that tend to fall out of these equations are not exactly 1 bit per second, but that's like plus or minus a couple orders of magnitude. So obviously, you can get any number you want by playing with those parameters from 0 to infinity. But so again, this is not something rigorous, but if you pinned me down and said, what do you think molecular communication is capable of in the end, I would say about 1 bit per second. That would be my answer. So now this is interesting because of the conversation we had this morning, that under very realistic assumptions, the bit rate seems to be on the order of 1 bit per 30 minutes. So I think that is reflected in the fact that I'm making some very aggressive assumptions about what the transmitter and receiver is capable of.
That was for communication by a signal transduction pathway, which is a whole, chain of events involving enzymes interacting with other enzymes.
Right.
Diffusion might or might not have anything to do.
I see.
So
This is
the
just
diffusion
strictly-
part of it
yeah.
might be limited to 1 bit per second, and the enzyme catalysis parts of it
Could
might
be
be
limited
an
again.
order of magnitude
That's right.
slower.
That's right. So what I'm arguing is that the diffusion limited part of it
Yeah,
is
yeah,
probably
yeah.
limiting it to about a bit per second.
That's interesting. So that's probably sensitive to parameters that vary by orders of magnitude
Yes.
across different biological systems.
Yes.
For instance, Nick mentioned in the synapse, you have cells sending action potentials to communicate to each other across synapses. Where in some cases, I don't know, in the cerebellum, you've got firing rates of like 100 hertz. And each of those is going to be potentially triggering synaptic release. So you might have communication mediated by diffusion across the synapse, which is, tens of nanometers and maybe fairly high diffusion constants.
Yeah.
That's in the order of 100 bits per second.
Yes.
Or you might not. It might be that, it's not clear how sensitive
Right.
the timing is of the receiver and stuff like that.
That's exactly right.
So, but it'll be interesting to look at specific examples.
Right. So the reason why I give this number is two reasons. Firstly, it provokes conversation. So every time I throw this number up, everybody's like, "What?" But the other reason is, so this constrains it to orders of magnitude. So I'd say probably plus or minus 2 orders of magnitude is probably reasonable here. But basically what I'm saying is capacity is not gigabits per second, and it's not 1 over gigabits per second. So
Yeah, if you're talking to electrical engineers who are wondering what the future holds for nanoscale, this is probably a good
it's probably a good guideline.
bucket of cold water to pour over there.
Not necessarily. So I mean, with 1 bit per second, you can actuate. It's probably appropriate for control.
You may have multiplicity, so you might have a lot of these devices communicating
That's
in
right.
parallel.
Yeah.
In which case, and that also happens in the nervous system. You have, the time constant for response of an individual nerve cell might be 20 milliseconds to sort of get its input together and generate an action potential.
Yeah.
But there are situations where a neural population will have sub-millisecond response times because there's 100 neurons kind of getting common input,
Yeah.
and some of them are closer to the threshold than others, and the first one that goes carries the population signal.
Yeah, that's right.
Right, so there's all kinds of weird stuff going on.
Absolutely. So, but just like single link, diffusion limited.
Yep.
Is what the question right here.
With stem cells in the synapses, there are a lot of ways that the system narrows down the timing of the event,
Okay.
so that the event happens pretty quickly after synaptic release and stops almost immediately afterwards.
I see. So that would then boil down to more of the diffusion limited.
Right.
Is what you're saying.
Yeah.
Rather than just one molecule diffusing in the synapse.
Right.
Right. Well, one extreme version of the delay selector channel, which is probably a different limit than the one that you took, and would give a different bound, is if you imagine taking a large number of molecules but releasing them all simultaneously.
Yes.
So
Yes.
that you could get the timing of that. If you had agreed ahead of time that you were going to release them all at once in a bolus, which is how most biological systems that I know of organize their signal.
That's interesting.
Right? Then you could get a much sharper rise and much higher, and if it was sort of quiet before that point, and then boom.
Right.
And then how quickly can you make those things decay?
Yes,
So
that's
once
the
you fire the next
reuse
one.
time is also critical.
Yeah,
here.
so how many can you get together, right? How many molecules of glutamate can you pack into a synaptic vesicle, and how quickly can you suck them up on the other side?
Yeah.
Might be the two, and how narrow can you make the cleft? Those might be like the key things that determine how far the nervous system can push the capacity on a person's basis.
Right. Yeah.
But having the synapse also act as an integrate and fire type of method rather than just something that's responsive to a single element.
Right. Yeah, that's also.
Good enough. And
So yeah, as far as mechanisms for exactly how this would occur, yeah, that's something I'd like to look at as well. So that would be interesting.
Cool. Well, let's thank our speaker, and he's around for a little while longer for questions, but those who need to go should feel free to come. So, thank you.
If you're interested in what I do, there's the website.
So then you
And